Okay, so we're going to be looking at connected particles. The idea of this topic is that whereas before you may have been looking at an object or a particle which is moving under a force and therefore being given some acceleration, now we're going to look at having more than one object. So two or more objects or particles, and these objects are connected in some way, which can be either they're directly touching each other, or they've got something connecting them, like a string or a tow bar or something like that. So that's the idea of this topic. So yeah, let's just clarify what we mean by connected particles. So what's commonly sort of imagined when you're thinking of connected particles is something as simple as, say, you've got a box, and it's sitting on a table, and there's, say, another box, say it's a slightly smaller one, and the idea is they are connected. So they're connected in this case, for example, with a string. Okay, so that's one particular example of connected particles, and you could imagine that these will move as one sort of system. So if I move the box on the right to the right, then it's going to pull the box on the left along, and likewise if I move the box on the left to the left, then it's going to pull the other box. Okay, so the string in some way is connecting them. That's the idea there. The other sense in which you can have connected particles is, let's say, for example, I've got a box here, and then let's say I've got a smaller box sitting on top of it. Okay, these are also connected, so they're just touching effectively. So because they're touching, they therefore count as connected, which makes sense because if you imagine, let's say I move the bottom box upwards, then the little box is going to move up with it as well, isn't it? And similarly, if I move the bottom box downwards, then the box on top is also going to follow suit, or at least if there's gravity, it's going to sort of stay connected to it in some sense. All right, so there's a connection going on while they're touching, they're connected. And then similarly, if you've got a string between two objects, they're also connected. Okay, so that's generally what we mean by connected particles. So then while we're on the topic of strings, it's worth just reiterating a few facts about tension in a string. So tension is a force, and it's effectively a force which acts throughout a string, and it's essentially that force that you experience when, say, let's say there's two people, and they're doing tug of war or something, and let's say they're using a rope, or you could call it a string, and when they pull, each person is pulling on the string, and the string is in some sense pulling back from both people. So whenever you see a string, you're going to usually annotate it with a force, a tension force, and it's going to come from both ends separately. So you'll have a tension force here, which is T, and another tension force here, which is T. And we label them both as T because they're going to be the same magnitude of force. They just act in opposite directions. Okay, so that's how tension acts on a string. It's always from both ends, acting inwards in a sense from the end of the string and then along it. And that's that force that you experience when one thing's pulling on the string, the tension's pulling back. Okay, and that will also be happening even if the objects are moving. So let's say I'm pulling on the box on the right. As I do that, let's just put this back into position. In fact, I'm just going to delete this green table. Okay, if I pull on the box on the right, then what's going to happen is this tension, you're still going to have this tension in the string, right? The T on the right hand side is still pulling back on the box, and the tension on the left is also still pulling on that other box. And if the whole system is moving to the left, same again. You've always got this tension in the string, and it's always going to be equal, right? What will change is the value of the T. When the system is sitting still, and by system I mean the whole thing, when it's sitting still, you'll have one tension. When it's moving this way, at some acceleration, you may have a different tension. But the individual two tensions, these two, will always be the same. Okay, so now let's dive into an actual example. So we've got two particles, P and Q. They've got masses, 5 and 3. They're connected by a light, inextensible string. You're going to see this wording a lot, light and inextensible. The reason those words are important is because the word light means that the string has no mass, which means that the total mass of the whole system is going to be 5 plus 3, 8 kilograms. And that simplifies our calculations when the string has no mass. And it will always be the case that the string has no mass. And then the second adjective we've got here is inextensible. All that means is that effectively the string, it's not like an elastic band or a rubber band. When I pull on the string, it just immediately starts pulling from the other end. So there's no delay, if you see what I mean. If you imagine if it was stretchy, then when I pull one end, it takes a while before the other end starts moving. So that's not the case. So light and inextensible are just two sort of magic words which will always appear, which just tell us that it's a very simple scenario. The string has no mass, and it just works. It just transfers this pulling energy straight away. Okay, and let's look at the rest of the scenario. So it's pulled by a horizontal force of magnitude 40 newtons along a rough horizontal plane. It's rough, so that means there's going to be some friction going on. Particle P experiences a frictional force, there we go, of 10 newtons, and particle Q experiences a frictional force of 6 newtons. Okay, so let's just draw the scenario out first. Okay, so what I've done is I've drawn the sort of two yellow boxes connected by a blue string, and they're sitting on a green surface, which is the ground. It's some sort of rough surface. I know the question says particles, which implies they're sort of dots, but I've drawn them as boxes here only because then it's going to be clearer when I label forces on this diagram. It's going to be clearer where they are. If I try and put a bunch of arrows on a dot, it can get difficult sometimes. Occasionally, if you are doing a force diagram and it's a particle, it's fine to use a dot. It just depends on the scenario, really. Okay, so let's start adding forces onto the diagram. So let's see what we've got. So we've got P. I should label it really. Let's say this one's P and this one's Q. This one's P is 5 kilograms. So that means there's going to be a force of 5 times the gravitational constant g, which is 9.8, remember. 5g is the weight of P. Okay, its mass is 5, but its weight is 5g. And Q has a weight of 3g. That's the force there. What else have we got going on? So P is pulled by a horizontal force of 40 newtons. Okay, so let's swap these around slightly, just to so this makes a bit more sense, because P, we're going to say, is going to be pulled, and I want the system to be going to the right, so I'm going to swap these round so it makes a bit more sense. So that one's Q, that one's P, and P is being pulled to the right by some mystery force. You know, somebody could be pulling it, or maybe it's got like a rocket booster or something, but that's 40 newtons to the right. And then it's also got friction of 10 newtons, so there's 10 newtons pulling it back. Okay, and Q also has a frictional force of 6 newtons, and it's pulling it back. Okay. Now, if I wanted to sort of be really precise in forces, I should really, technically, include the fact that there's going to be a reaction force here as well on Q. Because we know that the particle or the box is not falling through the floor, so it's not moving up or down. So there's going to be a reaction force of 3g to match the downwards force of 3g. And similarly, because we know the box is not moving up or down, it must be in equilibrium vertically. So again, we've got 5g going up. And is there anything missing? There's going to be tension force on the string. So there's going to be some tension force, and we don't know what it is yet. I'm just going to call it T. And similarly, as we said before with strings, there's two tension forces effectively at each end. It's also a tension force of T. Okay, and this should then be all the forces. Okay, and then we're going to think about the forces in the vertical sense and in the horizontal sense. In the vertical sense, nothing interesting is happening, because when I look at the vertical forces, that's the 3g and the 3g here, they cancel out, and the 5g and the 5g here, they cancel out. So vertically, there's zero forces overall. There's zero net force. There's zero net force on Q, there's zero net force on P. Q and P are therefore not accelerating up or down, which makes sense because they're sitting on the table. Okay, so the interesting stuff is happening in the horizontal. So that's what we actually care about. So let's look at part A now. Find the acceleration of the particles. So in order to do that, we're going to use F equals ma. Okay, and that's a big part of really most mechanics questions. Let's look at Q and ask what is the total force. Okay, and just to clarify that we're talking about horizontally, I'm going to just add and this is an official sort of notation, in brackets put a little arrow. So this means I'm resolving horizontally, and not only horizontally, I'm saying right is positive. Okay, so on Q, what are the forces going horizontally? We've got T going to the right, and we've got 6 newtons going to the left, and because it's left, I'm going to do minus. Okay, so that's the force on Q. And that must be equal to its mass times acceleration. Now the mass of Q is 3, and its acceleration we don't know. I'm just going to call it A. Now let's look at P. We've got 3 horizontal forces on P. We've got 40 to the right. Okay, so that's the force. I'm just going to call this FQ, meaning force on Q, and FP, force on P. This is equal to 40 to the right, minus 10 to the left, and minus T to the left. So in the first case it was a plus T, in this case it's a minus T because they're going in different directions. And again, this is equal to the mass of the object, which in this case is 5, and then times an acceleration. I'm just going to move this diagram to the right a bit, just so we've got a bit more space. Oh dear. Okay, now one thing I want to highlight is this. This is really important that we understand this. This force here is obviously not the same as this force here, right? Because this is the force on Q, that's why I labelled it FQ, and this is the force on P, and I labelled it FP. So why then was it acceptable for me to just say I've got here an acceleration A and here an acceleration A and use the same letter? Really, should I not have said this was the acceleration of Q, AQ, and this one's the acceleration of P, AP? That would be the technically correct thing to do. However, the reason we don't need to do that is because they're connected. So if you think about it, when P is moving to the right, Q is going to be following it along because of the string. And what that means is, as P accelerates, it's getting faster and faster and faster because there's a force acting on it. Q is also going to accelerate in exactly the same way. So the acceleration of P and Q are the same. We still don't know what that value is, but we know it's going to be the same acceleration for both, even though there's different forces acting on them, right? That's because they also have different masses. So it takes a different amount of force to produce the same acceleration for different masses. So this is the useful fact here, that the acceleration is actually the same. So that's meaningful that we use the letter A in both cases. Now the problem is, individually these equations aren't going to be able to tell us the acceleration, and the problem with that, and the reason for that, is because we've still got this unknown tension. However, notice this: if we add these two equations together, what am I going to get? So I'll have t minus 6, let's do the left hand side, t minus 6 plus, and then let's do the other left hand side, 4t minus 10 minus t, and that's equal to, now let's do the right hand side, 3a plus the other right hand side, 5a. And now you can see that the t's are going to cancel, right? There's a t and here's a minus t, so they go away. And all I'm left with is 4t minus 10 minus 6, which is 24. And on the right hand side, 8a. And that implies that a equals 3. And we've got our answer for the first part. A is equal to 3. Now, if you wanted a very quick way of doing this, of getting that answer without having to do these sorts of separate parts, okay, just consider that you could have, instead of doing the separate parts and then adding them together, we could have straight away jumped to considering the system as a whole. So remember, we call the entire connected particle thing, we call that the system. So for the whole system, we could say the following: the force acting, the overall horizontal force, so I'm saying it's horizontal with the arrow, that is equal to, and then we could just add them up. We could say, okay, I've got 40 to the right, I've got minus 10, I've got minus 6, and these two t's, I can straight away see they're going to cancel out because one goes right, one goes left. So I'm not even going to bother including them. So I'll just go straight away to saying 40 minus 10 minus 6. So then I could straight away jump to just writing here 40 minus 10 minus 6 equals 24. And then similarly, what is the mass of the whole system? So the m, that is 8, because we've got 5 plus 3. 5 plus 3, if we're talking about mass, it's just 5 plus 3, give me 8. So then we've got, again, F equals ma, and that implies, that's an F there, that implies that 24 equals 8a, and that implies a equals 3. Okay, I haven't done anything different really, it's exactly the same logic, except this way we've just jumped straight to the answer a bit more quickly without having to separate it into considering Q and P separately. Although we should still be able to do that. Okay, hopefully that makes sense. So now we want to find the tension in the string, part B. Let's go back to the separate formulas we had for a moment. So we had this, didn't we? We had t minus 6 equals 3a, and effectively 30 minus t equals 5a. Now that we know a equals 3, we can just plug that in. Let's do the first one. Okay, if I do the first one, let's see what we get. We would get t minus 6 equals, and then 3a is 9 because a is 3. That implies t equals 15. And we've got the answer. But just to check that this is all making sense and that, you know, effectively the maths isn't broken, let's look at the other one. We've got 40 minus 10 minus t, so that's in other words 30 minus t equals 5a. 5a is 15. So then again that implies, oh okay, t equals 15. Okay, so it doesn't matter which one you ended up using, they'll both give you the correct answer. The tension is 15, and that also sort of makes it clear the symmetry here. This t is in fact the same as this t, but that's not, you know, a coincidence or anything. It'll always be the case, at least when, you know, the string is light and inextensible. The tension is the same at both ends. Great, so we've answered the second one. T is equal to 15. And then the final part, part C, I talked about that already a bit really, didn't I? About these key words light and inextensible. So let's just write down precisely, what should we be saying, if I want to tell someone why these words are important. What assumptions are these associated with? And it's as follows. The mass of the string is negligible. In other words, we treat the mass as 0. And the tension is the same throughout. And in the case of it inextensible, what that lets us assume is that the masses accelerate at the same rate. Right? So the two particles are both accelerating at the same acceleration, which is where I was talking about those two formulas both using the same value for A. Yeah, so that's what those two imply. Okay, so let's talk a bit about Newton's third law, and we want to be very careful here because this is something that I feel like has quite a few misconceptions associated with it. Now, the statement of the law that people are used to hearing, which is sort of almost the shortened form, is that for every action there is an equal and opposite reaction. And I think it's a little bit vague when it's just expressed that way. For every action there is an equal opposite reaction. I mean, first of all, what exactly do we mean by action, right? So I think it's far more helpful to, instead of thinking action reaction, to just think for every force there is an equal and opposite force. Okay, and the words equal, opposite mean equal. In what sense? In what sense do we mean equal? We mean equal magnitude, and we mean opposite direction. Okay, and this is quite an interesting law because think about it. What it effectively says is, if there's ever a force going on, there's a force acting on an object somewhere, you know for an absolute fact there will be a second force which has exactly the same magnitude and is facing in the complete opposite direction. And that's always the case. So forces always come in pairs. They always come in pairs. That's effectively what this law is telling us. And I think part of the confusion of this law, or where people misapply it, is when they'll see two forces and maybe they have the same magnitude, they might even be opposite, and they'll just immediately say those are equal and opposite forces, those are a pair of forces. But it's not always the case. The pairs can sometimes be a little bit confusing, and I think a good example to just try and ensure we don't fall into this misconception is the example of an object just sitting on a table. Okay, so I'm just going to briefly talk about that. Okay, so here we've got a picture of a table, red table, and a yellow box sitting on top of it. And I want to draw a force and then think about what its pair is. Okay, the first force that I'm going to draw is the weight of the box. Okay, so assuming it's a uniform box, evenly distributed mass, then technically the weight is coming from its center of mass in the middle. So let's draw this force here, okay? And this is the weight of the box, okay? So we've got a force there. It's acting downwards. It's got some magnitude. And now ask yourself, what do we think is the equal and opposite force in this scenario? And what you probably, well, it depends how good you are really, or how prepared you are for this question. You might have said it's the reaction force of the table pushing back on the box. That's not the equal and opposite force. It happens to be equal and opposite, but it's not the equal and opposite force. Think about what is causing the weight. Is the table causing the weight on the object? It's not, right? The equal and opposite forces always act from one object to another object and in reverse. So what are the two objects involved in this weight? This weight is acting on the box, and it's caused by the gravity of the Earth. So there's actually a third hidden object in this whole picture. It's planet Earth. Okay, so I'm just going to approximate the curvature of that. Okay, there's Earth. Okay, the box is being pulled by Earth, and additionally, the Earth is being pulled by the box, which is something we sometimes forget about, right? Gravity is a two-way thing. Okay, so Earth is pulled by box. Okay, the only thing is, because the Earth is so massive, literally it has a huge amount of mass, it doesn't really go anywhere. It hardly moves, right? The force is the same amount, but remember, the more massive an object, the less it accelerates when the same force is applied. So an object will fall because of the weight induced by the gravity of the Earth's pull, but the Earth is barely going to be moving by the gravity of that box. So that's the equal and opposite force in that case. Then we've got a second pair of equal and opposite forces. We have the reaction force of the table pushing up on, let's say this, okay, we've got the table pushing up on the box, okay, so that's reaction. And additionally, we've got the box pushing on the table. Okay, so this is a box pushing on table. And I suppose if we really wanted to be precise, we'd have to add a third pair, right? Which would be there's the weight of the table. It's a bit hard to add now. Let's just add it here. Okay, so we've got another weight, which is the weight of the table. And again, you've got an equal and opposite, Earth pulled by table. Okay. It's getting a bit messy now. The main thing I really just want to illustrate to you is that you have to be careful when you think about this equal and opposite forces rule. Okay, it's not necessarily as obvious as you might think. Okay, but do be confident that every force has an equal and opposite force. It just might not be the force that you think it is. In this scenario, if the box is in fact not moving, it's sitting on the table, then yes, that blue arrow is the same magnitude as that green arrow. They are equal magnitude, and they do happen to be opposite. But that's only because the box isn't moving, and they are not the official equal and opposite pair. The equal and opposite pair are these two green arrows. Okay, and then these are another pair, and these are another pair here. Okay, that's a common misconception, so try not to fall into that trap. Okay, and then one last bit of not actually using maths, just because I really want to make sure that you're conceptually getting the idea of how the equal and opposite forces work. So I suppose I could draw a picture, but what I'm really asking you to do is to just kind of visualize a scenario for yourself. So that scenario is you've been in an elevator before, maybe not the one in LAE, but you have been in an elevator, and there's you, and you're in the elevator. So you enter the elevator, picture yourself entering the elevator, and it's not moving yet. And what do you feel? What do you experience? You probably don't really feel much of anything, right? And what's going on is that there's your weight, whatever that may be, okay? And remember, the equal and opposite force to that is gravity, is the Earth being pulled by you, effectively. Okay, so you're pulling the Earth. That's the equal and opposite force. And then there's also the lift reaction force, so that's pushing up. Okay, Really, I should be placing that arrow here. Okay. So they happen to be equal. Okay. These are not equal and opposite forces. Okay. They've got the pair that corresponds to each of these is somewhere else. Okay. I know I keep saying it, but this green weight has a second force, which is you being pulled by Earth, and this yellow force, which is the lift pushing on you, that has an opposite force, which is you pushing on the lift, but I haven't drawn that one. Okay, so these are the two forces that are acting on you: Earth pulling you and the lift pushing you up. Right now, those forces are the same, so you don't really feel much. Then I don't know, you go into the third floor, you press the 3, the lift starts moving up, and you can tell when the lift is moving, right? You have that sensation. You have that sensation. You don't have to be seeing anything. You don't have to be looking out a window or seeing stuff moving. You can feel when the lift is going up. And the reason you can feel it is because there is now a net force on you, which is not 0, right? You've begun accelerating. So at least at first, right? Eventually, maybe the lift will not accelerate anymore and go at a constant speed. But for the small moment that it's accelerating, that yellow force, which is the lift pushing you up, which is the reaction force, that has increased for a little bit. Okay? And as you know, if the yellow is bigger than the green in magnitude, that means there's a resultant force. Okay? And if there's a resultant force, that means there's acceleration. It means you're accelerating upwards. Okay? Eventually the elevator, if it was moving up for a very long time, it might settle into a constant speed, at which point that yellow force will get a bit smaller and it'll become the same magnitude as the green force again. Okay? But whenever you feel movement, that's you feeling acceleration. And I guess what I'm really trying to illustrate here is that this yellow force, this reaction, it really is not the same as this weight. It can change independently of it. Okay? So, in a roundabout way, these are definitely not equal and opposite forces. That reaction force can change, and it changes depending on how the lift is moving. Cool. Okay, so let's look at an example now. And hopefully it will be less confusing precisely because you thought long and hard about these equal and opposite forces. Okay, so here we've got effectively a lift. And the lift has two objects inside it. And the lift itself weighs effectively nothing. Okay, how do we know that? It says here it's light. So we're going to say it has no mass. So it's a light scale pan. The scale pan is this triangle bit. It's attached to a light inextensible string. That's this bit here. And it's got the two masses. And there they are. And they're sitting on top of each other. It's all connected, right? Because the string is connected to the scale pan, and the two objects and the scale pan, they're all touching each other at their various surfaces. And the other bit of information, which is not drawn on the diagram, is that the whole system is accelerating. Okay, so we've got an acceleration, and that acceleration is 0.5. Okay, remember it's a double-headed arrow, so it indicates its acceleration. The acceleration is 0.5. Okay, so similar to what we just talked about in the lift, the whole thing is accelerating, so therefore don't assume that reaction forces are the same thing as weight, are equal and opposite to weight. They may not be. Okay. Right, so let's see what we need to do first. We need to find the tension in the string. Before we do that, let's, in as much detail as possible, draw the forces that are going on in this system, because I want you to really fully understand what the forces are that are involved. Okay, so I've just drawn the whole thing a little bit bigger so that we can see the forces a bit more clearly. Let's think first about, okay, this 400 gram object A. Okay, so that's the top yellow box. What is its weight? Well, it's 400 grams. That's 0.4 kilograms, so it's 0.4 g. It's a little bit confusing this G. This G means grams. This does not mean the gravitational constant G. So don't get confused by the fact that I'm now about to write 0.4 G on this thing. Okay, that means 0.4 times the gravitational constant, that's the weight, and this 400 grams, that's the mass, but I've converted the mass into kilograms first. So 400 grams equals 0.4 kilograms, and if I convert that mass into a weight, it's 0.4 G, where G is 9.8 here. Okay, so that's the 0.4 G downwards. And then what is the reaction force of the bottom box pushing up on this one here? Okay, well, let's just do it like this. Okay, what's that going to be? Not 0.4 G, okay, because these are not equal and opposite forces. That 0.4 G is the Earth effectively pulling the little box. This other arrow I've just drawn going upwards, that's the big box pushing the little box. So they're not related forces. So I don't know what it is. I'm just going to label it as R1. Okay, reaction force 1. Okay, and there's no other forces acting on the little yellow box. It's got a weight and it's being pushed up by the bigger box. That's it. Okay, and then what about the big box? So the big box has a weight of 0.6 G. And again, there's a reaction force. Okay, now there's multiple reaction forces here, isn't there? There's the lift pushing up on the big box. Okay, there's the lift pushing up on the big box. Again, I don't know how much by. I'm going to call it R2. Okay, there's no reason to believe it's going to be the same as R1, right? This is not a pair of forces. It's just some reaction force. I don't know what it is. And then there's a third force, which is acting on this big box. What do you think that might be? It's going to be the little box pushing on the big box. So in other words, the opposite force to this R1, right? So in fact, I think, is it helpful? No. Yeah. Let's do it. I'm going to change that R1 to a different color. Hang on. Okay, so that blue R1 has its friend, the equal and opposite force, which is acting this way, and that's acting on the big box at the bottom. So we've got big box pushing up the little one with R1, little box then pushing down the big box with R1. These are equal and opposite. This 0.4 G, it's a weight, and the opposite forces for weight is just affecting the Earth. So we don't care about the opposite force for this one. It's somewhere off the picture. Same with the 0.6 G here. And for this R2, so that's the lift pushing up the big box. So I guess technically that one also has an equal and opposite friend. So let's rename that or recolor that R2 to green. And the lift itself has got a reaction force R2 acting on it. That's the big box pushing down on the lift. Okay. What other forces are there? There's the weight of the lift itself, but that's 0 because it's a light scale pan. The scale pan has no mass effectively. And the other force, I've run out of colours now, but is going to be the tension here. Okay. Is the tension pushing it up. What do we think the equal and opposite force of this tension is? It's not pictured, but it's going to be wherever the other end of the string is hanging from, the ceiling or wherever, it will be the other tension heading the other way, right? So again, every force has this equal and opposite force. It's just sometimes it's not included in the picture, okay? So to summarize, the red forces, I haven't included their equal and opposite friend in the picture, whereas the two blue forces, they're equal and opposite friends, and the green forces are also the equal and opposite pairs, okay? And every force is one object acting on another. Right, So hopefully that's clear in the diagram. These kinds of like lift problems with weights inside them, they cause endless confusion because, and I think part of that confusion is just misunderstanding the way we've got these equal and opposite forces. So it'd be all very well if I just went through the calculation immediately, but I think much better that you can understand these equal and opposite forces first before we just launch into the actual numbers. You know, if you look at the textbook for this question, it makes it look so simple, but I think that sort of hides the deeper complexity of what's going on with some of these forces. Right, so we've got that picture. I'm going to set that to one side, and then we're going to actually try and answer the question. So, find the tension in the string. Let's consider the whole system. I'm going to resolve vertically. Let's say up is positive. Okay, and I'm going to do the whole system. So, let's basically add up all the forces that we've got going on, but wherever there's an equal and opposite pair, we know they're going to cancel out, so I won't bother including them. So the first one we've got is T. That one's acting up, so we've just got T. Then we've got the blue R1 acting up, but there's also an R1 here acting down, so these cancel out. So instead of writing here plus R1 minus R1, I'm just not going to include it. Then we've got minus 0.4G, and it's minus because it's acting down. Okay. Then we've got an R2 here, but again it's got a pair here in the opposite direction, so I'm not going to bother including these. I won't include those. So then I'm just going to include also this 0.6G here. Okay, cool. So that's the whole system. That's the net force acting on the whole system. What's that equal to? So that's F, right, the resultant force, time, and then that's going to be equal to mass times acceleration. So m times acceleration. The acceleration is 0.5, so this is 0.5 m. And what is m? M is, if we're talking about the whole system, then we have to add up the mass of everything. The string has no mass, it's light. The scale pan has no mass, it's light. So then we've just got 400 grams plus 600 grams. That's 1 kilogram. So the mass is just 1. So in other words, this is equal to a half. Okay, so that's T minus G, 0.4G minus 0.6G, equals a half. So T equals a half plus G, which is equal to a half plus 9.8. Or in other words, 10.3. So that's the tension in the string, 10.3 newtons. Okay, next. Find the force exerted on mass B by mass A. So it's on mass B and it's by mass A. So it's A affecting B. So just think, which of these forces on this diagram is this one? The A affecting B. And remember, we haven't actually labelled it. That's A, and the bottom box is B. Which force is A affecting B? It's going to be this force, the blue R1 going down. That force is A pushing down on B. Okay, so it wants us to basically find what's the magnitude of that R1. Right, that's the force of A pushing B. Now that happens to be the same thing as this R1, right? At least in terms of magnitude, the direction's different. So what we can do is, let's just consider the body A, right? I'm just going to remove this information here. Let's consider the body A. So this is my A, the top box, the 400 gram one. And there's only two forces on it, right? We've got the 0.4G down, and we've got the R1 going up. Okay, so then let's just do F equals ma again. All of this stuff is about F equals ma. So F, the resultant force on A, the total of all forces, is R1 minus 0.4G. That's equal to the mass of the object, which in this case is 0.4, right, because it's a 400-gram object, times the acceleration. What's the acceleration? Well, we worked out the acceleration of the whole system, or not worked out, sorry, we were given that, 0.5. The acceleration of the whole system is going to be, because it's connected, the acceleration of A. So it's just going to be 0.4 times a half. That's our MA. In other words, 0.2. So now we have the fact that R1 is equal to 0.2 plus 0.4 G. So put that in a calculator. What's 0.2 plus 0.4 times 9.8? You get 4.12. Oops, 4.12. So that's the answer. It's 4.12 newtons. Okay, and remember, this R1 here, that is not the force exerted on B by mass A in the sense that it's not actually that force. It's this one, right? But it just wanted the magnitude of the force, so it'll be the same as working out that one. Okay. Again, all of this, you look in the textbook, it'll just do this in 2 lines and say, done. It's 4.12. Perhaps it makes sense to you. It's that innate. But personally, I think you really need to make sure you understand this image, because otherwise you're going to be muddling a lot of the forces that are going on in this image. Right, okay, last one. Find the force exerted on mass B by the scale pan. Look at the image. Which force is it talking about? Mass B is being affected by the scale pan. So it'll be this one, right? This green R2, the one pacing upwards. That's the scale pan pushing up the object B. Okay, so we want to find that one. So probably then realized that would also be the same as just working out this R2 down here, right? So again, I think in this case we've got 2 options to us, and since we've got the time, I'm gonna actually explore both of them. Okay, so let's do these one by one. Just clear some space. So I think the first and easiest way is to use the scale pan as our body of reference and the forces that are acting on that. So we've got tension going up, and what else? We've got the R2, which is the big box B pushing on the scale pan. And that's it. Remember, the scale pan has no weight. So those are the only 2 forces that are actually acting on the scale pan. So when we do F equals ma, we end up with T minus R2, resolving upwards, is equal to, alright, so what's the mass of the scale pan? What's ma going to be? Think about that. It's going to be 0, because the mass of the scale pan is 0. So therefore, we end up with T equals R2. Or I could say R2 equals T, which implies that R2 is equal to, and in this case, same as the first answer, 10.3. Yeah? So that is the force exerted on mass B by the scale pan, 10.3. So that's our answer, but let's just do it the slightly more complex way, but hopefully this will illustrate that everything should always be internally consistent. Okay, so instead of considering the scale pan, let's consider the big box B. Okay, so this is the big box. What are the forces acting on the big box B? We've got the R1, which is A pushing on B. We've got the 0.6 G, which is the Earth pulling on B. And we've got, I'll just draw it, no, I'll draw it still here. R2, which is the scale pushing on B. So those are the 3 forces acting on B. Let's resolve what's F equals ma. So we'll have R2 going upwards, minus R1 downwards, minus its weight, 0.6 G. Okay, and that's equal to Well, what's the mass of the object? Is 0.6, and the acceleration is still a half. Okay, so it's 0.6 times a half. Now, R1, we worked that one out earlier, didn't we? That was 4.12. So we should be able to then say R2 minus 4.12 minus 0.6g is equal to, and then let's simplify the right hand side to 0.3. So R2 is equal to 0.3 plus 4.12 plus 0.6g. And that's equal to, check it on your calculator, 10.3. Okay, so same answer. So this will always work. This will always work. You'll always get the same answers as long as you've got a good understanding of the forces involved. Okay, and then you'll be a lot happier with yourself if you can see that you're always getting the same sort of answers. Cool. All right. So I know it was a bit long to go into that much detail for what seems like a simple question, but hopefully it will be worth it in the long run. It'll then make it easier to understand the practice questions. So I've got 4 questions for you to try. I think I've sort of spoken enough. I'm not going to give you too many hints. Instead, I'll just let you give them a go, and you can always ask questions if you need to. So here's the first question. If you want to give it a go, pause the video now. And your answer is here. Okay, and next question, give it a go, pause the video now. Okay, and there's your answer. Next one, pause the video now. Okay, and the answer. And finally, now we're really getting into sort of the depth of things. Here, instead of using a string as a thing that connects an object, we've got here a light tow bar parallel to the road. Effectively, treat it as a string. It has tension. So give that one a go. Pause the video now. Okay, and the answer is here.